A collision is a short-duration interaction between two objects. In this video, I will focus specifically on inelastic collisions. A perfectly inelastic collision is a collision in which two objects stick together and move with a common final velocity. Since we are just learning the basics in this video, we will stick to perfectly inelastic collisions in an isolated system. An isolated system means that no net external forces act on the system. An isolated system is necessary in order to have the conservation of momentum. The conservation of momentum means that the total momentum of the system, which is the vector sum of the momenta of individual particles, does not change. This means that the initial momentum equals the final momentum. After an inelastic collision, the objects move together with their combined mass. Since momentum equals mass times velocity, using the conservation of momentum, we can fill in the blanks of the equations to solve for whatever variables we need. Here's an example. I slid a metal box towards a motionless cardboard box. After the collision, the two boxes move together. Let's pretend that this is a perfect physics world where friction does not exist. Since the initial velocity of the cardboard box is 0, and I can find the final velocity of the system using the meter stick and a stopwatch, if I use a balance to find the mass of both boxes, then I can find the initial velocity of the metal box using the conservation of momentum. So here are the masses of the boxes that I found beforehand, and also the final velocity of the two-block system. Then we just plug all our variables into the equation and solve. Let's apply these ideas to a problem. A 300-gram bird flying along at 6 meters per second sees a 10-gram insect heading straight toward it with a speed of 30 meters per second. The bird opens its mouth wide and enjoys a nice lunch. What is the bird's speed immediately after swallowing? We know both objects are initially in motion. The bird eats the insect, so the collision is technically when the bird swallows the insect because at that point they are moving together, which makes this an inelastic collision. Start by writing down all variables. Then write down the conservation of momentum equation and plug in variables. Then we just simplify and solve. Now let's try a problem where one object is initially at rest. A kid at the junior high cafeteria wants to propel an empty milk carton along a lunch table by hitting it with a 3-gram spitball. If he wants the speed of the 20-gram carton just after the spitball hits it to be 0.3 meters per second, at what speed should his spitball hit the carton? So we can assume that the spitball will stick to the carton because it is not stated otherwise. If the spitball sticks to the carton, that means that the spitball and carton will move together after the collision, which means that it is an inelastic collision. So the carton and spitball should have the same final velocity. Again, we start by writing down the variables, both known and unknown. Then we use the conservation of momentum equation to solve. We know that the carton starts with 0 velocity, so we can cancel out that term. This is pretty much the only thing that changes when one object starts with 0 velocity. Now let's explore collisions at an angle. In class we learned how to solve elastic collisions at an angle, but did not do the same for inelastic collisions at an angle. Here's a scenario. As you can see, mass 1 is initially moving in a horizontal line, and mass 2 is moving at an angle. After the collision, they move together with the combined mass of m and a final speed of vf. To solve problems relating to this scenario, we need to find the x and y components of the initial velocities of the masses. We use trigonometry to do this. However, in this case, the initial velocity of mass 1 is horizontal, so we don't need trigonometry for that part. Then we plug everything in to find the initial x component of momentum. Then we do the same for the y components. In this case, the initial velocity of mass 1 does not have a vertical component, so we'll just write that in as 0. Then we'll just do the same thing with the final velocities and use that to find the x and y components of the final momentum, this time using the combined masses of m1 and m2. To recap, When dealing with perfectly inelastic collisions, use the conservation of momentum. When dealing with inelastic collisions at an angle, we're still using the conservation of momentum, but remember to use trigonometry to solve for the x and y components of velocities and momentums. Thanks for watching. I hope this video was helpful.